interstellar travel and discussing about that in today's event. I'd like to give you a little bit of an indication of like Dr. Conley Powell. He holds a BA in physics from Berea College and an MS in engineering science from the University of Tennessee Space Institute. Got a Ph.D. in mechanical engineering from the University of Kentucky. He is a member of the technical staff at 4M Research in Huntsville and has been a faculty member at the Space Institute and worked with the Arnold Engineering Development Center near Tullahoma, Tennessee. He's worked with locally, there's Teledyne Brown, we have BAE Systems here, we've got Analytical Services and Davidson Technologies in Huntsville. I've heard of all those companies being around here. And Dr. Conley has also taught graduate courses in subjects ranging from astrophysics to nuclear engineering. He specializes in space trajectories, attitude dynamics, space propulsion, and numerical analysis, but has also worked in the area as diverse as hypersonic aircraft, gravitational fields, ionic beams, nuclear fusion, and interstellar flight. He's currently writing 3 textbooks on orbital mechanics, nuclear rockets, and numerical analysis. Wow. Please welcome Dr. Conley Powell as we hear.
Right there it is. Very good. Let me make it clear at the outset that I am quite convinced, quite sure, that when we build our first Starship, it will look nothing like anything we can imagine today. And if other races are building Starships, I'm quite sure that they look nothing like anything.
They're not hearing you.
Does he have the microphone?
Yeah, well, that's the problem that they were saying. So in the back, they can't hear you.
Can we just try it? Can we sit there?
Try and put it up there a little bit closer.
Is that any better?
Better? No? No, they're not hearing.
In that case, maybe we should do it the hard way.
Yeah.
What the, it's just the speakers back there don't work. Yeah.
Now, do you read me?
Is it the speakers?
Try it again.
How are we doing now?
Better?
Are we
Better
okay?
somewhat. Check a little bit, I guess.
Yeah.
Are we okay now?
Rich. Yeah.
Well, to retrace my steps, I'm quite sure that when we finally build our first Starship, and I hope it won't be too awfully long, it will be nothing like anything we can imagine today. And I'm also sure that if other races are building Starships today, they are nothing like anything we can imagine today. However, this is a statement of faith. What I would like to do today is attempt to answer, or at least provide a partial answer, to the question, what can we do with propulsion systems that we are reasonably confident we can actually build and in the immediate future? This will establish a worst case. If we can do this well, then we can almost certainly do better, and others are probably doing better today. It's intuitively obvious that there is an optimum initial acceleration for a given mission. If your initial acceleration is too low, then you take too long to build up speed, and your flight time is longer than it should be. If, on the other hand, your initial acceleration is too high, then you are devoting more mass than you should to your propulsion system and less mass than you should to your propellants, and your maximum velocity is not as high as it should be. It is less obvious that there is an optimum exhaust velocity. If the propulsion system is one for which the exhaust velocity is a design parameter. as is the case with an ion drive or a plasma jet. The reason is that the amount of power that it takes to produce a ton of thrust is more or less proportional to the exhaust velocity, and therefore, presumably, the mass of the propulsion system per unit thrust is more or less proportional to the exhaust velocity. So if your exhaust velocity is too high, then you are necessarily going to devote more mass than you should to propulsion and less mass than you should to propelling. Let's take as the simplest possible case a parallel stage Starship that flies a one-way mission over a given distance. And let's suppose that it has a given even number of stages, half of which we use for acceleration, half of which we use for deceleration. And let's suppose that the propulsion system mass to exhaust power ratio is given, that the tank mass to fuel mass ratio is given, and that the exhaust velocity and the initial acceleration and the stage burning time are the same for all the stages. The problem is, what is the optimum exhaust velocity and what is the optimum initial acceleration? And if we can't actually deliver the optimum exhaust velocity, and maybe we can't, then what's the optimum initial acceleration? And what's the minimum flight time? At the first equation there is the flight time, is an expression for the flight time as a function of the number of stages, n, the stage burning time, delta t, the distance for the mission, d, the exhaust velocity, v sub e, and the initial acceleration, a sub 0. The stage burning time is given by that rather complicated expression in the second equation. I won't go through the derivation, it's pretty straightforward. Now, the flight time is a function of 7 variables, and we can simplify things by doing a little non-dimensionalization like this. We use the distance and the power to mass ratio, alpha, mass to power I should say, to non-dimensionalize the exhaust velocity, the initial acceleration, the flight time, and the stage burning time. We get the expressions in the last two equations. Now, if we optimize the non-dimensionalized exhaust velocity and the initial acceleration and the flight time, assuming that we have a total of 10 stages, and that the tank mass to fuel mass ratio is 5%, that's not an important quantity. We find first that the flight time is not at all sensitive to the payload fraction. You can increase the payload fraction from 0.1% to 10%, and the flight time only increases about 50%. So we needn't trouble ourselves to build an enormous ship that carries a tiny little payload. We would do just as well, almost as well rather, with a reasonable payload fraction, say 1%. If the payload fraction is 1%, you see that the optimum non-dimensionalized exhaust velocity is 0.739. The optimum non-dimensionalized acceleration is 1.096. And the optimum non-dimensionalized flight time is 1.925. Well, what do these non-dimensionalized quantities translate into for a mission to, say, Alpha Centauri? Here we vary the power to mass ratio, or the mass to power ratio, I keep inverting it, and we show the exhaust velocity and the flight time. If we could achieve a mass to power ratio of 1/10 of a kilogram per megawatt, then our optimum exhaust velocity would still be less than 1/5 of the speed of light. and the flight time would be 33.4 years. Evidently then, even if we had total conversion, we would not need exhaust velocities higher than a fifth of the speed of light unless we could build propulsion systems with what appear to be enormous power to mass ratios. In fact, if the mass to power ratio is as high as 10 kilograms per megawatt, the optimum exhaust velocity goes down to less than 12,000 kilometers per second, and the flight time goes up to 155 years. Many people will tell you, eventually, toward the end of his life, J. Allen Hynek came around to this point of view, I think mostly due to the malign influence of Jacques Vallée, that UFOs are not alien spaceships after all, but interdimensional manifestations, whatever that may be, because interstellar flight is impossible or at least impractical. Well, whether it is impractical or not depends on whether you think that a trip to the nearest star lasting 100 years or so is something that no rational being would attempt to do. I have read too many science fiction stories about generation ships and suspended animation and so on and so forth to agree with Dr. Hynek on this point. And remember, we are talking about what we are reasonably confident can actually be done in the immediate future. What can actually be done in the more distant future is an entirely different question. After all, the first nuclear reactor went critical only 77 years ago. It would be a very foolish person indeed who would claim that he can anticipate the ultimate limits of technology today. Still, 100 years is quite a while, and 11,790 kilometers per second is still a lot of kilometers per second. The highest exhaust velocity that we can expect to achieve would be with systems that we can clearly envision today, would be delivered by a thermonuclear plasma jet. That is to say, a fusion reactor that ejects its reaction products plus unburned fuel, of which there unfortunately will be a lot, as a jet. In other words, the nuclear equivalent of a chemical propellant rocket. What sort of exhaust velocities could actually be achieved? I'll try to give you a reasonably good answer to that question in just a minute, but for the moment, if we had a thermonuclear plasma jet burning deuterium and helium-3 as fuel with 100% efficiency, and if we could convert with 100% efficiency all the energy released into exhaust kinetic energy, our exhaust velocity would be 26,500 kilometers per second. Is that high enough for the propulsion system to be acceleration limited rather than energy limited? Well, that depends on the mass to power ratio. And since we have not yet built a fusion reactor, it is very difficult to say what mass to power ratios are actually achievable. Fission reactors can deliver today about a kilogram per megawatt or a little less. Whether this figure has any relevance at all to the question of the mass to power ratio of a thermonuclear plasma jet, I will not speculate. We have supposedly, and by we I mean a lot of very smart people all around the world, supposedly been attempting to develop thermonuclear reactors for more than 60 years. We don't have one yet. Why we don't, I can only speculate. But I think no reasonable person would deny that the thermonuclear reactor will someday be a reality, and it may even turn out that a reactor designed for space propulsion will be easier than one intended for terrestrial power generation. At least Terry Kamash, the inventor of the gas dynamic mirror, thinks so. Now, suppose we cannot deliver the optimum exhaust velocity, which, as we'll see in a minute, is highly probable. How much do we pay in flight time by using a lower than optimum exhaust velocity? Well, as it turns out, the penalty isn't too severe. You can reduce your exhaust velocity by a factor of 10, and the flight time only increases by about a factor of 4. So an energy limited Starship powered by a thermonuclear plasma jet might not be such a bad thing after all, even if we can't deliver the exhaust velocity we would really like to have. Here is a highly simplified analysis of the particle and energy balance in a thermonuclear plasma jet. The important ionic species are listed at the top: protons, deuterons, tritons, helium-3 and helium-4 nuclei. And the important thermonuclear reactions are the 4 at the bottom: deuterium and helium-3, the 2 deuterium-deuterium reactions, and the deuterium-tritium reaction. Almost all the effort in the thermonuclear programs around the world to date has been devoted to that 4th reaction, the DT reaction. The reason is that you can achieve a self-sustaining reaction at a much lower plasma temperature and with a much shorter confinement time with DT than with the other 2 fuel combinations. However, a DT reactor will not be at all satisfactory for spaceflight for a couple of reasons. In the first place, 4/5 of the energy released comes out in the form of neutron kinetic energy. This is going to be deposited in the reactor structure and could only be used by converting the thermal energy to electrical energy and feeding it back into the plasma. The effect on mass to power ratio would obviously be bad. And the problem of cooling the field coils, which presumably will be superconducting, would be very severe indeed. Besides that, tritium is radioactive and has a half-life of only 12.6 years. So if you start out with propellant tanks that are filled half with deuterium and half with tritium, long before you get to your destination, the tritium will mostly have decayed to helium-3, which would not be a bad thing. The DHE3 reaction is obviously by far the most satisfactory for propulsion purposes. Actually, at a sufficiently high plasma temperature, the reaction rate is higher than for the pure deuterium. Pure deuterium gives you a lot of neutrons also, as you can see from reaction number 3, and not nearly so much energy per unit mass as DHE3, so DHE3 is the obvious choice. Where do you get the helium-3? Probably by synthesizing tritium from lithium-6 in deuterium burning reactors and letting the tritium decay to helium-3. At any rate, even if we do not have a fusion economy that can produce enough helium-3 for the space cadets' needs, helium-3 can still be mined on the moon, where it is deposited by the solar wind, and perhaps from the atmospheres of Jupiter and Saturn as well. The particle balance is shown here. Particle balance for protons is the first equation. That first term there is the rate per unit volume at which protons are generated in reaction number 1, the DHE3 reaction. Second term is the rate at which protons are generated by reaction number 2, and the third term is the rate at which protons escape from the reactor. Tau is the confinement time. Second equation is the particle balance for deuterons. There's a source term here because we're injecting deuterons into the plasma. S2 is the number of deuterons injected per unit volume and unit time. And we're burning up deuterons in all 4 reactions. And of course they're escaping from the reactor just like all the other species. Energy balance for tritium nuclei, particle balance for tritium nuclei, particle balance for helium-3 nuclei, and finally for helium-4. The number of electrons is given by the very last equation and is simply the number that is required in order to make the plasma electrically neutral, which it will be to a very high degree of approximation. Energy balance here. First, the energy balance on the ions. Q1 is the energy released by reaction number 1, Q2 reaction number 3, Q3 reaction number 3, and Q4 reaction number 4. The ions also lose energy to the electrons. The electrons are going to be cooler than the ions, a lot cooler, we hope, because most of the radiation emitted by the plasma comes from the electrons, not the ions. And we have here an expression for the ion to electron energy transfer rate. Now I'm assuming here, and this is a doubtful assumption, that all the ionic species have Maxwellian distributions at the same temperature. They probably don't. The protons and the helium-4 nuclei are created by fusion reactions, and they have high initial energies and probably are going to be nowhere near Maxwellian. But the reacting nuclei, the deuterium and the helium-3, are injected into the plasma and presumably have more or less reasonably Maxwellian distributions at more or less the same temperature. This is a fairly gross assumption, but since we haven't built any fusion reactors so far, some fairly gross assumptions are more or less unavoidable. The electron energy balance. The electrons gain energy by collisions with the ions, and they also radiate energy away. They radiate by 2 different mechanisms. In the first place, when an electron collides with an ion, it emits radiation called Bremsstrahlung, German word for breaking radiation. This is mostly in the X-ray region, and it escapes from the plasma. The plasma is transparent to X-rays. So this constitutes an energy loss mechanism that we could recover only by converting the thermal energy deposited in the walls of the reactor to electricity and feeding it back into the plasma. And as I've already indicated in connection with neutron energy losses, that's probably a bad idea because it would make the system too heavy. And then there's cyclotron radiation emitted by electrons spiraling around the lines of force of the magnetic field. The magnetic field is weaker inside the plasma than outside the plasma. As a matter of fact, if the plasma pressure to magnetic pressure ratio, beta, is 1, which is its maximum possible value, then the magnetic field is entirely excluded from the plasma, and there won't be any cyclotron radiation. One of the many reasons that the tokamak is not nearly as good a reactor concept as many people would have you believe is that it is limited to low beta, which means, among other things, low power density and very high cyclotron radiation losses. Still, cyclotron radiation is not necessarily a total loss, because unlike bremsstrahlung, which is X-rays, the cyclotron radiation is microwaves, and it can possibly be reflected from the reactor walls and absorbed in the plasma. So even if we cannot achieve beta equals 1, which with a tokamak we can't even come close to, even if we can't achieve beta equal 1, we aren't necessarily going to lose all the bremsstrahlung radiation. Still, I have assumed that we do. A pessimistic assumption. And finally, here's an expression for the power that goes into the reactor exhaust, and an expression for the exhaust velocity. When you work out all the numbers, it turns out that for a deuterium helium-3 reactor, the maximum achievable exhaust velocity is about 9,400 kilometers per second. A lot lower than that 26,500 kilometer per second figure for a 100% efficient reactor, and even lower than the optimum exhaust velocity for the highest mass to power ratio that I considered. So it looks like thermonuclear plasma jets are going to be energy limited, not acceleration limited, even for relatively high mass to power ratios. But as I have also shown here, lower than optimum exhaust velocity imposes a fairly small penalty on flight time. Well, that's what we can expect to do with a propulsion system that we are reasonably confident can be developed, if we really want to do it, in the immediate future. What we can do with more exotic propulsion systems, which are speculative at this time, I will not speculate about. I will leave that to others. But my subjective reaction to these results is that the interstellar spaceship theory of UFOs is not ruled out by any means. It would appear that if this is the best that anyone can do, and I am quite sure that this is not the case, but if this is the best that anyone can do, it is probable that no one will launch an interstellar expedition for any other purpose than colonization. If these figures are anywhere near the best that we can do, then it is difficult to imagine anyone flying back and forth between the stars for any reason, conquest or transportation of agricultural products or anything else. Colonization is on this view, colonization is the only reasonable objective for interstellar flight, and that would imply that if UFOs are alien spaceships, then somewhere in the solar system there is a colony. We have been as far as Pluto and have found no clear evidence, despite those who believe that the face on Mars is really a face, and I had a very good friend who was quite convinced of that. We have found no clear evidence that we are not alone in the solar system. The implications of this are that either UFOs are not alien spaceships, or B, that interstellar flight is an awful lot easier than I have indicated here. I personally lean toward B, but again, this is a statement of faith. And there you have it. Any questions?